Dear students, after studying this module, you shall be able to know the symmetry element and the symmetry operations in stereochemistry. You should also be able to understand the various types of symmetry operations which are performed on a vast number of molecules, or to say organic molecules, which are known to us. We shall also learn about the different point groups and comprehend their classification, and also identify the point group in various common organic molecules known to us. Let us now begin with the introduction of this topic known as elements of symmetry or symmetry elements. Stereochemistry, as we have already introduced, is a study of the relative arrangement of atoms or groups in a molecule in a three-dimensional space. Stereochemical isomers are molecules which have the same chemical formula and bond connectivity, but different relative arrangement in three-dimensional space. In contrast, constitutional isomers have same molecular formula but different bond connectivity. Sometimes it becomes extremely difficult to determine with increasing molecular complexity to determine the non-superimposability of a compound with its mirror image. Thus, what do we require in case of this problem if the complexity of a particular molecule increases? Thus, a mathematical concept known as the group theory can be applied to determine the symmetry elements in a molecule. There are 4 symmetry elements which need to be considered for this purpose. In this module, we shall focus our discussion on the symmetry elements and the symmetry operations which are performed on various molecules in organic chemistry, and they help us to know the superimposability with the increasing complexity of the structure with its mirror image. Let us now discuss in detail the symmetry elements and operations. All the molecules can be described in terms of their symmetry. In order to study the symmetry of a molecule, certain operations such as rotation and reflection are performed. And if by doing so an arrangement is obtained which is indistinguishable from the original molecule, the operation is said to be a symmetry operation, and the molecule is said to possess an element of symmetry defined by the operation which is performed on the molecule. Molecules may contain symmetry elements. They can be either point, line or plane elements of symmetry, and reflection, rotation and inversion as the symmetry operations thereby. These are tabulated in this table. As you can see, the symbol for the identity is E, the symbol for symmetry plane element is sigma, the symbol for inversion center is I, the symbol for proper axis of element of symmetry is Cn, where n can be 360 degree by n and the rotation is given by that number of times, that is n number of times. Improper axis, this is denoted by Sn. We are now first of all going to deal with the identity element of symmetry. Identity is the simplest symmetry operation which is present in all the molecules. If a molecule has only symmetry element identity, that is no other symmetry element is present apart from this one, then it would be asymmetric. It does nothing to the molecule which is original in the structure. As you can see here, this molecule which has all the halogen atoms like chlorine, bromine and fluorine and one hydrogen, that is tetrahedral in nature, this has only the identity element of symmetry, and this operation is performed, and thus the molecule is obviously asymmetric. Let us now begin with the proper rotation symmetry element, which is Cn. The rotation operations, both proper and improper, occur with respect to line called an axis of rotation. A proper rotation is performed by rotating the molecule 360 upon n, where n is the order of the axis along which it is rotated or the molecule is rotated. If after rotation resulting in configuration, structure is indistinguishable from the original structure, we say there exists an n-fold proper rotation axis or Cn axis in the molecule. Molecules may contain one or more proper axes. Let's talk about the simplest molecule, or you can say the water molecule in consideration. If we see, it has a C2 axis, or what I mean by this is, if we rotate the water molecule by 180 degrees through this axis, we get a identical molecule again. Thus, the value for n for water molecule will be 360 degrees divided by 180 degrees, because after every 180 degree rotation you get a similar molecule. So, n here would be 2. Thus, Cn in case of water molecule will become C2. Let us now talk about ethane molecule. Ethane contains both C2 and C3 axis, depending on the axis that is in consideration. Now, if you see here and consider the C3 axis in ethane, that is when there is a horizontal axis. If we rotate the ethane molecule by 120 degrees along the horizontal axis, through this axis we can get an identical molecule after 3 rotations, that is Cn would be 3 or C3. However, if we look at the C2 symmetry in ethane, then we would consider it like this. Just like the water molecule, it is a vertical axis. If we rotate the ethane molecule by 180 degrees, then we will get an identical molecule again. Thus, 360 divided by 180 degrees will give you a value of n as 2 or Cn as C2. Thus, we can see that even one molecule can have 2 axes of symmetry depending on the rotation axis, whether it is horizontal or vertical. However, such an axis is not possible in case of water molecule, but it is possible in case of ethane molecule. Let us now talk about the trans or cis 1,2-dichloroethylene, which contains a C2 proper axis. Now, you can see here, in all the cases when you rotate this molecule, you will only get a C2 axis. Let us now talk about a more complex molecule, benzene. Benzene contains C6, C3 and C2 proper axis of symmetry. Now, you can see here the C6 axis in benzene, which is a vertical axis which passes through the plane of benzene. However, if you see the C3 axis in benzene, it passes through one of the bonds, and like this you will get an indistinguishable molecule after the C3 arrangement, that is again 120 degrees. If you again see the C2 axis in benzene, there can be 2 arrangements. When the axis pass through the carbon atoms of the benzene ring, or when the axis pass through the bonds of the benzene. So, there are 2 types of C2 axis in benzene, that is C2 dash and C2 double dash. After having studied the rotation axis, we will now concentrate our attention on the reflection operation denoted by the term sigma. The reflection operation can now be pictured as follows. Take each atom in the molecule and move it toward the reflection plane along a line which is perpendicular to that plane. Continue moving the atom through the plane at a point equidistant from the plane on the opposite side of the plane. If the resulting configuration is indistinguishable from the original, we say there exists a symmetry plane in the molecule. The ammonia molecule contains like this 3 identical reflection planes. All are designated as vertical symmetry planes, sigma V, because they contain the principal rotation axis in consideration. Now, you can see the 3 identical reflection planes in ammonia as shown to you here in the figure. Benzene, on the other hand, contains a total of 7 reflection planes, 1 horizontal plane and 6 vertical planes. This is also shown here clearly in the figure. The inversion center, that is the next element of symmetry that we shall talk about. The inversion operation occurs through a single point called the inversion center, and it is denoted by the letter I, located at the center of a particular molecule. Note that the inversion center may or may not coincide with the atom in the molecule. Each atom in the molecule is moved along a straight line through the inversion center to a point at an equal distance from the inversion center. If the resulting configuration is indistinguishable from the original, we say there exists an inversion center in the particular molecule. Now here you can see in the staggered configuration of the ethane, we see here there exists an inversion center. However, we can see here the inversion center in benzene is quite different. Similarly, there are other molecules in which you can appreciate the existence of inversion center, that is in the trans 1,2-dichloroethene and in trans 1,3,4,6 dichloro-dibromocyclohexane. Let us now, students, concentrate our attention upon the improper rotation, that is this element of symmetry, that is also denoted by Sn. N is always in the subscript. An improper rotation is performed by rotating the molecule 360 degree divided by n, that is n number of times, followed by reflection through the plane perpendicular to the rotation axis. If the resulting configuration is indistinguishable from the original, we say there exists an n-fold improper rotation axis or the Sn axis in that particular molecule which is under consideration. Now you can see here in the staggered configuration of the ethane, you can see the improper axis, how it exists almost perpendicular to the bond. Again, see here the improper axis, that is the S4 in staggered ethane, and 3 S4 axes are there, and improper axis is S6 and S4 also occur in the same molecule. Point groups. Now, after having discussed all the symmetry operations and the symmetry elements in regard to various molecules and their study, we shall discuss the point groups. The molecular structures are almost infinitely varied. As you know, there are numerous molecules which are known to us right now. Nevertheless, they can be classified into a limited number of symmetry related categories known as symmetry point groups, or simply you can say point groups, on the basis of symmetry operations that can be performed on them. These symmetry operations or the symmetry elements combinedly form a group, and since each of the operations leave the center of gravity of the molecule unchanged or unperturbed, this group is known as the point group. There are several mathematical requirements for a symmetry operations to constitute a particular group, the most important one being the existence of certain binary relationships among them. Now you can see here for the classification of various symmetry elements and operations and into the point groups. So, a group of low symmetry, if yes, then it would have C1, Cs or Ci elements. If no, then it has a group of higher symmetry. Whether it has a group of higher symmetry, if yes, then it would have these symmetry elements. If no, then the highest order rotational axis Cn would be there. If perpendicular C2 axis is existing, then it would have D groups. If no, it would have C or S groups. And on the basis of that, various symmetry elements can be decided as shown to you. We have discussed a few examples below to help you students understand and find out the point groups of common molecules in organic chemistry. Now I shall take up these examples one by one, and I hope that you can appreciate the existence of point groups and symmetry elements by these examples. Example number 1, where we will discuss the symmetry elements in operation in case of allenes. Now you can see here there is a proper axis which is C2 axis in allene, and there is again a proper axis shown here. One is a horizontal and there are two vertical axes. Now there are improper axes denoted as S4 in the allene, and there are two sigma D elements of symmetry. How to decide the point group in allenes now? Now first question I would ask is the molecule linear? Obviously no. Second is, does the molecule contain two or more unique C3 axes? No, because it contains a C2 axis as described above. Is the molecule containing a proper axis of rotation? Yes, S4. Identify the highest order of Cn. Are there any perpendicular C2 axes? The answer would be yes. Point group may be DNH or DND or DN. These are denoted as this. The next question is, does the molecule contain a horizontal reflection plane denoted as sigma H? Obviously, it does not contain a horizontal reflection plane. So, no DNH. So, out of the possibilities of DNH point group, DND point group or DN point group, DNH point group is basically ruled out. Does the molecule contain n dihedral reflection planes? Yes, it does. So, sigma D element of symmetry. So, the point group obviously will become D2D. Thus, the point group in allenes will be D2D. So, you can see how we have ruled out various other possibilities and we have zeroed down to one possibility of the point group, and how you will decide like this in the other molecules also. So, in the second example, I take the water molecule, symmetry elements and operations in the water molecule. This is what we are going to discuss. So, as discussed above, the proper axis of rotation is C2 in case of water molecules, and there are two vertical planes denoted as 2 sigma V. So, the first question again would be linearity in the molecule. No, it is a V-shaped molecule. Does the molecule contain two or more unique C3 axes? No, it contains C2. Does the molecule contain proper axis of rotation? Yes, it does. It contains a C2 axis. Identify the highest order of Cn. Are there n perpendicular axes? That is, answer is no. No perpendicular axis. The point group thus may be C2V because of the perpendicular planes also, the vertical planes, or the C2H or simply C2. The next question is to rule out the two possibilities out of the C2V or C2H or C2 and zero down to one possibility. Does the molecule contain horizontal reflection plane sigma H? The answer is no. It contains a vertical reflection plane. Thus, no C2H. Final question, does the molecule contain n vertical planes? The answer is obviously yes. It contains the vertical planes. Thus, the point group of water will be C2V. Now you can see how by asking simple questions to yourself and analyzing the molecules in a better way, you can actually assign the point groups to a particular molecule. Third example is the symmetry elements and operations in trans 1,2-dichloroethene. Now, if you analyze this molecule, it has a C2 proper axis of symmetry and it has a horizontal reflection plane that is denoted by sigma H. So, thus we would ask to ourselves, obviously the first question, is the molecule linear? No, the molecule is not linear. Does the molecule contain two or more unique C3 axes? No, it does not. It contains a C2 proper axis. Does the molecule contains a proper axis of rotation? Yes, it does. It contains a C2 axis, the proper rotation axis. Now we have to identify after these three questions the highest order of Cn, which is 2. There are Now the next question is, are there any n perpendicular C2 groups? The answer is no. Thus, the three choices again just like the water molecule, C2V, C2H and C2. Now the question is, does the molecule contain horizontal reflection planes? Now the answer to this here, which is different from the water molecule, yes it does. It contains a sigma H molecule, sigma H reflection plane, horizontal plane. So obviously the C2V is ruled out and the C2 is ruled out. Thus the point group here will be C2H. Now fourth example students, the symmetry elements and operation in cis 1,2 dichloroethene. Now we have discussed the trans form of this molecule, now we are discussing the cis form of this molecule. Again the molecule is not linear, does not contain more than unique C3 axis, it contains again a C2 axis. However, the only difference students here in this molecule, the cis form of this 1,2 dichloroethane is just that instead of a horizontal plane, it contains a vertical reflection plane. There was a horizontal reflection plane in case of trans molecule, there is a vertical plane in case of the cis molecule. So, it contains a proper rotation axis, yes. Thus, the options would be C2V, C2H or C2. So, obviously, there is only a vertical reflection plane. So, C2H, the possibility of C2H is obviously ruled out, which was there in case of the trans form of the molecule. So, we would have C2 or C2V. So, it contains a horizontal reflection plane? No, it does not. So, does the molecule contain n vertical planes, sigma V? Yes, it does. So, out of the C2 and C2V, we only have zeroed down to C2V. Thus, the point group in cis 1,2 dichloroethene would be the C2V. The fifth example I would like to take is that of hydrogen peroxide. Obviously, again the molecule is not linear. The molecule contains no unique 2 or more C3 axis, right? There is a C2 axis. It does contain a proper rotation axis, C2 axis again. So, the option left with us is C2V, C2H or C2 again. So, does it contain a horizontal reflection plane or a vertical reflection plane? No, it does not. Thus, we are cancelling out the vertical C2V and the horizontal because it does not contain vertical or horizontal reflection planes. The only option left with us for the point group of the hydrogen peroxide is C2. Thus, the point group of hydrogen peroxide is C2. Taking the next example into consideration, we have the symmetry element and operations in case of cyclohexane, that is dibromo-dichlorocyclohexane. So, molecule is obviously not linear. The molecule contains 2 or more unique C3 axes? No, it does not. Does the molecule contain a proper rotation axis? The point group may be CS or CI or C1 if it does not. So, no, it does not contain any proper rotation axis because rotation in any kind of angle or any kind of rotation will not give you the same molecule because it is dibromo and dichloro substituted. Does the molecule contain a reflection center? No, it does not, neither horizontal nor vertical. Does the molecule contain an inversion center? Obviously, it does. When you invert the molecule, you will get the same molecule, indistinguishable. Thus, when it contains a inversion center, that is one in the center, you can see the dot in the center which depicts the inversion center. Thus, we can say that the point group in case of dibromo-dichlorocyclohexane would thus be Ci, denoted as Ci. So, now you can appreciate how asking simple question and how by knowing the reflection planes and the inversion centers and the proper axis of rotation, you can actually decide the point group in a particular molecule no matter whether how much the complexity of the molecule is. The next example students, the symmetry element and operations in case of Z, that is Zusammen 1-chloro-2-bromo-ethylene. The molecule is obviously not linear, you can see here. Does it contain 2 or more unique C3 axes? No, it does not. Does the molecule contain a proper rotation axis? Obviously, because it is substituted like this, it does not contain. Thus, we have 3 options, it is CS or CI or C1. Since there are no reflection plane, there is a reflection plane. The next question to ask is, does the molecule contain a reflection plane? So yes, it does. Thus, we can say that the point group here will be CS. The next and the last molecule is the symmetry element and operations in case of benzene as a molecule. Now you know that it has C3 and also a C2, two types of C2 axes. Now C2 dash and C2 double dash depending on where the axes pass through, whether from the bonds or the carbon atoms. And it also, you can see here in the picture, it has a horizontal reflection plane denoted by sigma h. So the molecule is not obviously linear, as you have studied the benzene molecule many number of times. Does the molecule contain two or more unique C3 axes? No, it contains two, that is C2 axes, two types of C2 axes. Does the molecule contain proper rotation axes? Yes, it does. Can you identify the highest order of Cn? Are there n perpendicular C2 axes? Then the answer is yes. So the point group may be DNH, DND or DN. So out of these three choices, we have to obviously rule out two, because it has a horizontal reflection plane, that is sigma h. So obviously the only choice is DNH. So the n here is 6, thus the point group will be D6H. So after having studied these molecules and telling you about the point groups and having studied various symmetry elements and the operations which are associated with it, we shall now summarize this module. In this module, students, we have taught you in detail about the 4 symmetry operations, namely rotation, reflection, inversion and reflection rotation or rotation reflection. These are described through which similar atoms and groups in a molecule can be interchanged to give arrangements indistinguishable from the original. 4 symmetry elements have been defined in terms of the above symmetry operations, which are a simple or proper axis of symmetry denoted by Cn, a plane of symmetry sigma, and an inversion center I, and an alternating or improper axis of symmetry Sn. The same symbols are used for symmetry operations and symmetry elements. The molecules have been classified into a number of symmetry point groups based on the symmetry operations that can be performed on them. Schemes for classifications, flow sheet diagrams and many examples of various molecules have been taken by us and have been cited in the module for clarity of the concept of the various point groups. And as you know, students, many of us find this topic very difficult of point groups and the classification of various molecules into the point groups, the symmetry elements and the operations that we have that is to be performed on various molecules having higher order of complexity. But after having described to you all these symmetry operations in great detail and after having taken so many examples, I hope you will find this topic now much more easier and much more friendly.